Dear Johann, I hope you are well. How are the wife and kids? I'm writing to let you know that I'm meeting with Sophie Germaine for the first time today. You know, I mistook her for a male for the longest time. She used to write to me under the pseudonym Monsieur Leblanc, but upon learning that she is a woman, you can only imagine my astonishment and admiration. It is indeed unusual that we should find ourselves a female mathematician in this day and age, and there are repercussions for a female to study mathematics. But if only people knew how bright she is, I think they would change their minds. Anyways, I wish you well. Tell Caroline I said hello. Yours, Gauss. Please, come in.
Good morning. Thank you for meeting with me.
The pleasure's all mine. Please, have a seat. You know, I just want to say the scientific notes with which your letters are so richly filled have given me 1,000 pleasures. I have studied them with the attention, and I admire the ease with which you penetrate all branches of arithmetic, and the wisdom with which you generalize and perfect. But I must ask, how did you become so well trained in the study of mathematics?
Well, to be honest, it was not easy. Growing up during the French Revolution and the years after were quite stressful. Fortunately, my parents were well off middle class citizens, so I was able to isolate myself in my father's library. It was there that I discovered mathematics, much to my parents' dislike. There was a time when my parents would freeze me in my bedroom in an attempt to put a stop to my studying. But my passion for abstract sciences and the mysteries of numbers kept me going, and eventually they gave in.
You know, it's so very rare to find someone of your courage and determination, especially given our customs and prejudices. Where was it that you studied?
Sir, I tried to attend Equal Polytechnique, but was unsuccessful due to my gender. So I mostly collected lecture notes to study and corresponded back and forth with Mr. Lagrange under the pseudonym Monsieur Leblanc, and later wrote to you under the same name.
I see. And was it around this time that you developed your work on elastic surfaces?
After corresponding with Lagrange and yourself, I saw Chotney in the early 1800s present a wonderful demonstration on vibrating plates. And so I spent the next 10 years working on a theory of elastic surfaces.
Amazing. And was it due to your work on elastic surfaces that won you the grand prize from the French Academy of Science?
Yes, sir. I had to submit three different copies, but my theory was finally accepted by the committee in 1816, which ended up securing my place in the French mathematical community.
Wow, your story is truly phenomenal. And anyhow, what is it that brings you here today?
Well, I've resumed studying number theory and I came across an interesting unproven theorem. Have you ever heard of Fermat's last theorem?
Fermat's last theorem is a theorem first proposed by Fermat in the form of a note scribbled in the margin of his copy of the ancient Greek text Arithmetica by Diophantus. In the note, Fermat claimed to have discovered a proof that the equation x to the n plus y to the n equals z to the n has no integer solutions for n greater than 2 and x, y, and z not equal to 0. But he never left behind a proof claiming that the margin was too small. In order to simplify his theorem, mathematicians were able to reduce it to just looking at prime powers bigger than 2. In order to simplify the problem further, we can assume that none of x, y, or z share a common factor, because if they did, we could cancel them. We can break the theorem into two cases. One, the prime p doesn't divide x, y, and z, or the prime power p doesn't divide exactly one of x, y, or z. It was case 1 that Sophie Germaine tackled with the following theorem, bearing her name. If p is an odd prime and there exists an auxiliary prime q of the form 2np plus 1, satisfying the following conditions. There are no consecutive pth power residues mod q, and x to the p is not congruent to p mod q for all x between 1 and q minus 1. There is then, in any solution to Fermat's equation, p squared must divide one of x, y, or z. This last part is exactly what case 1 of Fermat's theorem is about, but the rest of it's kind of confusing. Let's look at an example to help us better understand auxiliary primes and the non-consecutivity condition. As an example, let's look at the case where the prime power p is 5. When n is 1, then we have q equaling 11, and so we need to look at all the x values between 1 and 10, since q minus 1 is 10 in this case. In order to understand the phrase, there are no consecutive pth power residues mod q, we need to raise all possible x values to the pth power, or in this case, the fifth power. So we have the following set. Now reducing this set mod 11, meaning we divide all of these numbers by 11 and determine the remainders, then the result is... But hey, there are a lot of repeated values, so we can simplify this set to 110. And notice that 1 and 10 are not consecutive residues. So this is what Germaine meant when she said there are no consecutive pth power residues mod q. Thus, 11 is a good auxiliary prime for 5. Now what happens when n is 2? In this case, q is 21, which is not prime, so it cannot be an auxiliary prime. When n is 3, the fifth power residues mod 31 are 1, 5, 6, 25, 26, 30, mod 31. This fails the non-consecutive residue condition because 25 and 26 are consecutive residues. Thus, 31 is not a good auxiliary prime, which means we can also rule out n equals 6 and n equals 9 since they are multiples of 3. Applying similar steps to these remaining cases, we see that for p equals 5 and n between 1 and 10, we have that 11, 41, 71, and 101 are auxiliary primes. Now that we understand the vocabulary in Sophie Germaine's theorem, we can discuss her grand plan. If she could prove that there are infinitely many auxiliary primes for a given prime power p, satisfying the non-consecutivity condition, then there would have to be infinitely many primes that divide x, y, and z, which means at least one of x, y, and z is infinite, which is impossible because x, y, and z are finite integers. It turns out that Sophie Germaine was unsuccessful in her attempt because there are primes that have only finitely many auxiliary primes.
Prior to Sophie Germaine's attempt to prove the theorem for all primes, other mathematicians were only focused on specific prime cases. In fact, prior to Sophie Germaine's attempt, Fermat had proven n equals 4 case, sometimes before his death in 1665, and Euler had proven the n equals 3 case. Sophie Germaine then came along and drafted the Sophie Germaine's theorem. After Sophie's death, other mathematicians continued working on the problem with Dirichlet and Legendre proving the n equals 5 case independently, and Lamé proving the n equals 7 case in 1839. It wasn't until 1995 that Andrew Wiles proved the theorem is true for all cases using the machinery of the 20th century mathematics. In fact, the implications of his work are still being explored decades later. This means, compared to the other mathematicians, Germaine's approach was novel in that it was the first one that tried to tackle infinitely many cases at once. So we see that despite the barriers she faced as a female mathematician, she was able to achieve something that her male counterparts did not. This shows us that sometimes the greatest contributions happen when someone begins to look at a problem in a different way or try a technique that has never been done before. Germaine gave an example of something that did not work, which in turn let people focus on other solution paths. At the end of the day, solving Fermat's last theorem was a collection of failed solutions, new ideas, connections made by almost 350 years worth of mathematics.